Okay, so yeah, it was like 3 of glucose.
Yes, yes.
How much glucose is in glucose?
I'm pretty sure one of the palmitic acids was not supposed to be palmitic acid.
No, it was supposed to be palmitic acid, but it was the wrong number.
We fixed it.
So I haven't seen whether you guys did that correctly or not, but
How was the question? How much glucose is in glucose?
it was supposed to be ATP instead of glucose.
Yeah, I think we assumed that as well.
What's that?
The glucose inside of glucose, we did ATP.
Yeah, we did ATP.
Yeah, we did ATP. I'm pretty sure we caught on to what you were trying to say.
Yeah, that's scary that you're working at the same wavelength as me. So first question was how much ATP produced from one molecule of glycerol. So glycerol kinase. What did that reaction do? It's a kinase. Adds a phosphate to glycerol. And where's it going to get that phosphate? ATP, so that means minus 1 ATP. Then we had glycerol 3-phosphate dehydrogenase. Dehydrogenases generally indicate what is being used. Redox reactions. So there we have plus 1 NADH. Then we had glyceraldehyde, 3-phosphate dehydrogenase. That is also going to give us 1 NADH. At this point, we should have an intermediate of the glycolysis that is entering where the 3 sugar or 3 carbon molecule was entering. So you have the phosphoglycerate kinase. Sorry, this is where we entered the glycolysis. So glyceraldehyde phosphoglycerate kinase is going to produce 1 ATP. Pyruvate kinase is going to produce 1 ATP, plus it's also going to produce pyruvate. Pyruvate dehydrogenase and the citric acid cycle. When you go through that, you're going to have 4 NADH being produced. You're going to have 1 ATP equivalent being produced because you get a GTP out of the Krebs cycle, but that's equivalent to a ATP, and you get 1 FADH2 being produced. So if we look at the total, count up the NADHs, we have 6 NADH molecules. We have 1, 2, 3 ATP minus 1. So we have 2 ATP total. We have 1 FADH2 total. So 2 ATP is equal to 2 ATP. 6 NADH is equal to how many ATP? 15. So you get 2.5 ATP per NADH. 6 times 2 is 12. 6 times 0.5 is 3. So 12 plus 3 is 15. And 1 FADH2 will give us 1.5 ATP. So 1 glycerol molecule gives us the potential of producing 18.5 ATP molecules.
What is the fourth NADH?
So pyruvate dehydrogenase produces one. Then we have isocitrate dehydrogenase. We have alpha-ketoglutarate dehydrogenase, and we have malate dehydrogenase from the Krebs cycle. So that's 4 total. So what did you guys get?
I don't have the worksheet.
Yeah.
You have a picture of it.
If you look up the answer online, I find that it gives you a variety of different answers because they use different factors for calculating NADH and how much that is. Okay.
Rebecca just sent it to me. Because I asked it
This
for
is the
her-
correct answer that we should have gotten. This is what you need to answer right now.
I asked her for it last Wednesday, so I could just have to study. She was like, just nothing.
All right.
Oh my goodness, Rebecca, you're just dropping the ball.
Palmitic acid oxidation. So, palmitic acid, despite what the worksheet said, is a 16-carbon unsaturated fatty acid, which means you go through how many rounds of beta oxidation? Throwing up gang symbols. 7, right? Because if you need to cut it into 2 carbon molecules, you are going to need to cut it 7 times, because the last cut is going to give you the 2. You don't have to cut it 8 times. So you have 7 rounds of beta oxidation. So that means you're going to get 7 NADH. You're going to get 7 FADH2s. And you're going to get 8 acetyl-CoAs. 1 acetyl-CoA will enter the Krebs cycle and give you 3 NADH, will give you 1 FADH2, and will give you 1 ATP. So 3 NADH gives you times 2.5, 7.5. 1 FADH will give you, H2 will give you 1.5. 1 ATP will give you 1. So you get 10 ATP from this. So the 7 NADH times 2.5 is going to give you 17.5, right? 1.5, 7 plus 3.5 is 10.5. And 8 acetyl-CoA, each acetyl-CoA gives you 10 ATP, so that gives you 80 ATP. If you add this together, that's going to give you 108 ATP. But
Minus the 2. We did it. We fixed it.
but minus 2 ATP because the initial reaction that preps the synthetase, the fatty acyl synthetase, is going to take a ATP and make a AMP from it. So that gives you a total of 106 ATP equivalents. Which means for 3, how many ATP per carbon? So that was 106 ATP. And the correct answer, or the correct number of carbons, was 16 carbons. So if you did 16 carbons, you get 6.625 ATP per carbon, compared to 4, which is 31 ATP for glucose on average. Glucose has 6 carbons, and that gives you 5.167 ATP per carbon. So which of these is more efficient at producing ATP, glucose or fatty acids? The fatty acids. That should make sense to you, because how are we getting energy from the glucose and the fatty acid? What kind of reaction? Okay, so beta oxidation, and then for fatty acids, and then glucose is also going through an oxidation, right? But if we look at the potential to oxidize glucose versus the fatty acids have more potential to be oxidized, right? If you look at a glucose molecule, the oxidation state of the carbons is going to be less because they are connected to some hydroxyl groups, whereas in the fatty acid, the carbons are, for the most part, connected to hydrogens. So you have more oxidation potential in the fatty acids, meaning that you can get more energy out of them per carbon molecule. In addition to that, if we start looking at, so that was question 5, you get more with palmitic acid. If we look at how much energy you are getting per gram, so for glucose, that's 31 ATP in 180 grams. So you are getting 0.17 moles of ATP per gram for glucose. And for fatty acids, you're getting 106 ATP. For palmitic acid, that's 256 grams per mole. So you are getting 0.14 moles of ATP per gram. Yeah, it wouldn't be very efficient if you were getting 0.17 ATPs per gram of glucose.
Moles. We had 0.0 ATP. Before we changed it.
It's okay. The published paper that was published in an education journal that I sort of got the inspiration from actually was incorrect in saying that it was this many molecules of ATP per gram. So I was thinking about writing into the paper and correcting them, but it was like published in the 90s, so I didn't see the point.
They probably know by now.
Regardless of whether you used moles or molecules, for question number 7 then, if you do the ratio, you get 0.41 over 0.17, which is approximately 2.4 to 1, versus what is actually reported being 2.25 to 1 for the calories ratio. So this is the ATP ratio, this is the calorie ratio. The discrepancy, there's a few reasons why this might have some discrepancy. One is glucose does not equal all carbohydrate, and palmitic acid does not equal all fatty acids. So different fatty acids will give different amounts of energy. Certain carbohydrates can also vary in the amount of energy that they get, although there's going to be more variability in the fatty acids than it will be for the carbohydrates. The reason for that is that the length of the fatty acid per carbon molecule is going to give you the same amount of ATP because you're going to get the same amount of beta oxidation reactions, but you still only have the one initial priming reaction that uses the ATP to begin with. So if you start with a very short fatty acid, you're going to get a lot less ATP and then have to subtract 2 ATP from that. And then if you start with a longer one, you're going to get more of the ATP and have to subtract just 2 from that. So that is going to be part of the reason why there's a discrepancy. But so how'd you guys do?
I think we got. I think we just wrote down the wrong number for 3, but other than that.
Well, I'm going to give you credit for this because I messed up in my description or in the assignment that I gave you too much to actually take off, except for Brenna. I'm just going to take off anyway for her.
Yeah, other than
But-
that, number 6, we went into molecules. 'Cause we were all over the place.
Why did you start with molecules and then with moles?
Because when you do the 180 grams, it's grams per mole. And so this is 31 ATP per molecule. But when you figure this out, it's going to be how many moles per molecule of ATP. So you get this many moles of ATP.
See, we just went another step into molecules.
We did
We had
all
the
numbers,
same
numbers.
ratio and everything. It's just
Like, we did all-
molecules.
it's- I think we ended up.
We got what those ratios are.
Okay.
We have the
We
same,
did.
you got the same ratio, 2.4. So,
We just multiplied by avocados.
the avocado number.
Which would still, I mean, you can still get it correct there. It just, moles is easier to say than a huge number of molecules.
See that, but,
All right.
no, we had written down on the paper, we had 0.0 something ATP per gram.
Yeah.
So, and I was like, all right, there's a lot of them in there, not less
There's a
than one.
Hey, at least you intuitively realize that.
I had to argue my case, and I was like, one against the world, and I had no idea how to like say who's wrong.
One against the world, I was just doing again.
But we had the right answer if we just put mole.
We did,
in front of
yeah.
it.
I don't think we did.
All right. So, lipid oxidation and breakdown. Thus far, we have talked about the beta oxidation in the simple case when you have a saturated fatty acid. However, there's a couple of ways that beta oxidation can be complicated. First of all, you can have oxidation of unsaturated fatty acids. Now, this is going to require some additional molecules to actually function. So it will require an isomerase. What's an isomerase do?
Turns into a nice one.
Okay, so it's going to change it into an isomer. So you're not going to gain or lose any atoms here. You're just going to rearrange them. The isomerase is going to be used regardless of whether it is a mono or poly unsaturated fatty acid. If it is a polyunsaturated fatty acid, you're also going to need to use a reductase. So what is a reductase? Yeah, essentially. So It's the same thing as a dehydrogenase, except that it's, instead of being named after the thing that is being, let me think. So pyruvate dehydrogenase is naming it after the thing that's being oxidized, right? The reductase names it after the thing that is being reduced. But it's the same chemical reaction. It's going to be using a NADH, NADPH, or FADH2 as a intermediate. So what's going to happen here is that this isomerase converts the cis double bond to a trans double bond. You might want to wonder what the significance of that. The trans double bond that it converts it into is actually a intermediate in beta-oxidation. Remember that I said that our body has trouble handling trans isomers of fatty acids? Well, that's not 100% true. That was a slight lie. The slight lie. The trans fatty acids that our body has difficulty metabolizing, the issue is where that fatty acid or that trans fatty acid is. So with the trans fatty acid that is an intermediate in beta oxidation, the double bond is between the 2 and the 3 carbon. With the fatty acids that we have trouble with, the trans double bond is between like a 3 and a 4 carbon or something, some other location than that. So it's off by 1, and so our body does not recognize it correctly. So what's going on here?
That's a big
So we have our cis double bond here. The trans double bond is, or the isomerase is going to change it to a trans double bond, moving this to that location. And so we end up with this right here. We draw the hydrogens out just to further illustrate the point. You can see you go from a cis double bond to a trans double bond. So this then is an intermediate for beta oxidation, and it can enter the cycle and be used for energy. All right, if it is a polyunsaturated fatty acid, so 1, 2, has more than one double bond in it. The isomerase is going to function again to give us the trans double bond here. Now this can go through one round of beta oxidation and actually go through another round or half round of it to get it to a point where the molecule is going to function, that is ends up with this molecule here. So double bond, carbon. So notice that there's less carbons in between here. Now we've lost some carbons via the beta oxidation. So really, I should put it out in acetyl-CoA getting released here. This then has to go through a reductase. The reductase is going to take NADPH and turn it into NADP+. And so now we're going to lose one of these double bonds. The isomerase is going to put it in the correct orientation, and then it's going to go through beta oxidation. So I illustrated all this for you. What I want you to remember about the oxidation of unsaturated fatty acids is that it requires 2 additional enzymes in the case of polyunsaturated fatty acids, or one additional enzyme in the case of monounsaturated fatty acids. One of these enzymes is an isomerase that is moving the double bond around so that it's in the correct orientation. The other one is a reductase, which is removing one of the double bonds so that it looks more like a saturated fatty acid. But otherwise, it is going to be essentially the same as the saturated fatty acid beta oxidation, just has these additional steps. So it's like beta oxidation, but more complicated. So prior to today, we considered saturated fatty acids as the simple case, and we also considered fatty acids that have how many carbons in them? I mean, 16. 16 is what kind of number? It's an even number because acetyl-CoA is made up of 2 carbons plus the CoA molecule. So 16, 2 goes into 16 an even number of times, right? So we get an exact number of acetyl-CoAs. Well, it's possible to have odd number chains of fatty acids as well. With the odd number chains, what problem are we going to run into? We'd have a carbon left over, right? So with an odd number of fatty acid chains, it undergoes normal beta oxidation until 5 carbons are left. At that point, it is going to go through another cleavage, but this is going to be different. Cleavage of this 5 carbon molecule is going to produce an acetyl-CoA plus propenyl-CoA. Propenyl-CoA is going to go through a few reactions. It actually goes through more than the arrows that I'm drawing, but I don't want you to get lost in the details here, so I'm simplifying it. Ultimately, it is going to form succinyl-CoA. Where have we seen succinyl-CoA before? So the citric acid cycle. So this is then used by the citric acid cycle. So that's how our body handles odd number fatty acids. For the most part, most of the fatty acids that you encounter on a daily basis is going to be the even number. However, you do encounter some odd number fatty acids due to, odd bacteria metabolizing fatty acids and a few other things going on here. So that's why your body needs a way of handling these odd numbered chain. Again, it's just normal beta oxidation plus 3 additional enzymes to get to here. So what I want you to recognize is that it goes through normal beta oxidation until you have 5 carbons left. Cleavage of that produces propanyl-CoA plus another acetyl-CoA, and then that propanyl-CoA is converted into succinyl-CoA and used by the citric acid cycle. So don't get lost in the details. Those are the basic ideas that I want you to recognize with it. All right, so this brings us to the regulation of fatty acid metabolism. So fatty acid metabolism needs to take into consideration both that you don't want synthesis of fatty acids and the breakdown of fatty acids to occur simultaneously, because that would be a waste of resources. It also has to take into consideration whether you're using glucose for fuel or or if you have excess glucose that you need to store as fatty acid molecules. So we're going to kind of go through what happens to fatty acid synthesis really quickly in kind of just a brief overview and focus on the regulation that's occurring within the breakdown of it. So dietary carbohydrate is going to play an important role in the regulation of fatty acids. First of all, dietary carbohydrate can form glucose. I'm going to make that longer. And then glucose can go through glycolysis and pyruvate oxidation to form acetyl-CoA. So you may have noticed that acetyl-CoA is kind of an important player here. It is an intermediate in both glucose oxidation as well as carbohydrate metabolism, glucose catabolism as well as fatty acid catabolism. Having dietary carbohydrate is also going to influence your blood glucose levels. So if you have high blood glucose, how does your body respond? It's going to secrete insulin, so it's going to increase the concentration of insulin in your blood. One of the consequences of high insulin is that it is going to activate a phosphatase. The phosphatase is going to regulate this enzyme known as acetyl-CoA carboxylase. So ACC is acetyl-CoA carboxylase. This is the main enzyme that is regulating fatty acid synthesis. So the phosphatase takes the inactive form and turns it into the active form of acetyl-CoA carboxylase, and the acetyl-CoA is then converted into malonyl-CoA, which is the initial substrate for fatty acid synthesis then. All right, so if high blood glucose levels is going to turn on the ACC, what do you think will turn it off? Okay, so if we have low blood glucose, that leads to the secretion of what? Glucagon. And if glucose is gone, that in turn is going to activate some enzymes such as protein kinase A and AMP kinase that will then take the ACC, AMP sensitive kinase, take the ACC and convert it back into the inactive form. So low blood glucose, you're not going to want to take the acetyl-CoA and convert it into malonyl-CoA. Instead, you're going to want to use the acetyl-CoA for either the synthesis of carbohydrates or in the Krebs cycle for energy. So the acetyl-CoA here can really have two fates that depend on whether this ACC is active or if citrate synthase is active. What is citrate synthase? Yep, that's the first enzyme of the citric acid cycle. So the citric acid cycle is going to be regulating by citric acid synthase. This is going to be turned off by high levels of ATP, NADH, or acetyl-CoA. So generally, if you have high ATP levels, you don't need to make more ATP. So you turn this off and you say, okay, I'm going to use this acetyl-CoA and store it for when I do need more ATP. And so it gets converted into the malonyl-CoA for fatty acid synthesis. On the other hand, if you have low blood glucose, you're not going to want this to be running and storing the acetyl-CoA, as that low blood glucose generally indicates that you are active, and so you're going to want to use the acetyl-CoA then for citric acid synthesis. There are certain situations where you may actually need both energy and also have low blood glucose, that this is going to be metabolized differently. We'll talk about that in more detail next time. Now, malonyl-CoA in and of itself is also going to be regulating an enzyme. So it inhibits CAT1. What was CAT1 responsible for? Carnitine acyltransferase. What was the carnitine used for?
That's a good question.
So it's a transferase. What's a transferase do? Transfers things. So we have the carnitine. We have your fatty acyl-CoA. We swap out the CoA for the carnitine. We did that so that we could put the fatty acid where? Where does the breakdown of fatty acids happen? What produces most of the ATP in your cell? The mitochondria. Yeah, there we go. So the Cat1 is doing this reaction. So now that the acyl-CoA, the fatty acyl-CoA, or fatty acyl carnitine moves into the mitochondria, and now things are happening down here in the mitochondria that you can't see. So the Cat1 is taking the fatty acid CoA and substituting that. This goes into the mitochondria then, and then it immediately uses Cat2, so Cat2 to take the CoA and put it back on and get rid of the carnitine. So now you have the fatty acyl CoA. Again, the fatty acyl CoA then goes through beta-oxidation. Beta-oxidation produces acetyl-CoA, which then is going to be used by the Krebs cycle.
It's really all just circles.
Yes, it's a giant circle. Now, beta-oxidation itself is going to be regulated by a few things. So acyl-CoA, when you have a lot of that around, it's going to inhibit beta-oxidation. You don't need to make more acetyl-CoA if you already have a lot of acetyl-CoA around. And then the NADH to NAD plus ratio. When that is high, that is also going to inhibit beta-oxidation. Does that make sense why it would do that? When are you going to have a lot of NADH around? You have a lot of NADH around when you are actively breaking down glucose and fatty acids and have the Krebs cycle running, but what isn't running? What uses NADH? The electron transport chain, right? So the electron transport chain, that doesn't run when you lack oxygen. So if you don't have oxygen, you can't get energy from fatty acids because you can't use the Krebs cycle anyway, because the electron transport chain is not going to run, right? So you want to shut down the beta-oxidation so that you can come back here and conserve this and make the pyruvate convert into lactic acid instead. So you're shutting down fatty acid metabolism because that's going to use up what little NAD plus you have when you need to make more of that to keep the Krebs cycle running. So when this is high, you don't want to do fatty acid breakdown. More than you ever wanted to know about the breakdown of fatty acids, I'm sure. All right, looking ahead, no quiz this week, probably a quiz on Monday. Any questions? All right, guys, have a good week.